Assalamu alaikum. Dear, I am going to start the matrices basis. So, what is the matrix? Matrix is simply a array of number enclosed in a pair of bracket, like 1, 2, 3, 4. This is a matrix. And in the similar way, this is also a matrix 1, 2, 3, 4, 5, 6, 7, 8. It's called the square matrix. It's called the rectangular matrix. What is the square matrix? In a matrix, this horizontal line called the row. So in this matrix, this is the row 1, we can say that R1. This is the row 2, we can say that R2. The horizontal line in a matrix is called the row. And in the similar way, the vertical line like this one, this is the column, this is the column, this is the column. In this case, this is the C1 column and this is the C2 column. So this matrix contains two rows and it contains two columns. So its order is 2 by 2. The first number shows the row and the second number shows the column. So this matrix has order 2 by 2. Order or size means that how many rows and columns are there in a matrix. If in a matrix the number of rows and columns are equal, then we say that our given matrix is square. Like in this example, this is a square matrix. This is a because this matrix has this is R1 row and this is the R2 row. So we have two rows and this is the C1 column and this is the C2 column. So we have two rows and two columns. So it's a square matrix. The other types of the matrix is rectangular, in which the rows and columns are not equal. So this is the column matrix. This one, like it contains one row. It's contain this one row R1, and this is the second row, which is R2, and it contains three columns C1, C2, and this is the C3. So the rows are 2 and columns are 3. So its order is 2 by 3. So it's not a square matrix. It's a rectangular matrix. What is the advantage of square matrix and rectangular matrix? So square matrix have these advantages. We can find inverse of square matrix. We can find determinant of square matrix, which is usually denoted by if A is any square matrix, then its inverse is denoted by A inverse. Its determinant is denoted by in this way. Its adjoint is denoted as in this way, ADGA of A. So for square matrix, we can find inverse, we can find determinant, we can find adjoint, we can find the characteristic polynomial P lambda of A, we can find the eigenvalue, which is the lambda 1, lambda 2, lambda 3, and up to so on, and we can find the eigenvector. But in rectangular matrix, there are the lots of limitations, like it's difficult for us to find the A inverse. We can not find the determinant. Determinant not possible. Determinant not possible in square matrix. Not possible. In the same way, the adjoint is also not possible. If determinant and adjoint is not possible, then we can say that its inverse is not possible. And if its inverse is not possible, we can say the other thing also, which is the its characteristic polynomial P lambda of A is not, we cannot find the P lambda of A for this rectangular matrix. We cannot find the eigenvalues of a rectangular matrix. We cannot find the eigenvector of a rectangular matrix. Now I am going to discuss three more types of the matrix. The first one is the diagonal matrix. So what is the diagonal matrix? Just look here. We have this is a square matrix. In a square matrix in which all the elements are 0. Before starting the diagonal matrix, just look here. In this matrix, this 2, 4, this entries, as I shown here, is called the main diagonal. Main diagonal. So in matrix, in any matrix, this thing is actually the main diagonal. He says that a matrix, a square matrix, in which all the elements are 0, like this is 0, this is 0, except this main diagonal, this one, and at least one element of this main diagonal is not 0, like this one. It's a diagonal matrix. It's also a diagonal matrix. And it's also a diagonal matrix 2, 0, 0, 1. It's also a diagonal matrix 5, 0, 0, 6. So these are the diagonal matrix. So the next definition is a scalar matrix. In scalar matrix, this element 5 and 5, this 0 and this 0, the element on the diagonal are same. Just if there is a 5 here, then there is a 5 also here. So this is the scalar matrix. And in the same way, if these elements are 1 1, then we can say that it's a uh, identity matrix, or we can say that it's a unit matrix. Identity or unit matrix is usually denoted by I2, but it's a identity matrix of order 2 by 2 because it contains two rows and two column. This is the row R1, this is the row R2, this is the C1 column, and this is the C2 column. After that, we have the next thing, which is the I have discussed now the uh, identity. So what about the I3? I3 is the diagonal matrix of order 3. It's an identity matrix of order 3, like 1 0 0 0 1 0 0 0 1, which means that the element on the diagonal are 1. If the element on the diagonal are same other than 1, then we can say that it's a scalar matrix. And in the same way, this 1 0 2 and this 0 this 0 this 0 this 0 and this 0 and this 0, this is the diagonal matrix also. So I have teach you diagonal matrix, scalar matrix, and the next definition is about the identity or unit matrix. Now I will discuss some cases of a matrix, like how can you add, subtract the matrix. Like you have any two matrices, this matrix A, this matrix B. These two matrices are equal if their order is same. Like if A has order 2 by 2, then the next matrix also has order 2 by 2. So you can look here, it's order 2 by 2 and its order is also 2 by 2. So these two matrices are equal if their order is same, first condition. The second one is if their corresponding elements are equal. What is the corresponding element? These two, and element in the second matrix, the element at the same position, these two are same. And in the similar way, element on this position and element on this position are same, and element on this position and element on this position are same, and element are this position, element on this position are same. Then we can say that these two matrices are equal. After that addition, don't forget these things. Just to look here example, just look on the example. So here you have A matrix, this matrix A, this matrix B. You can add any types of matrices, you can subtract two types of matrix, but for addition and subtraction, the order of the matrix must be same. For addition, you add the corresponding elements, like this element added into this element added into this element added into this. In the similar way, 4 is added to 3, 5 is added to 0, and 6 is added to -2. In the same pattern, we can subtract two matrix. So when you add this 1 plus 2 become 3, 2 minus 1 become 1, and this 3 plus 4 becomes 7, this 4 plus 3 becomes 7, this 5 plus 0 becomes 5, this 6 plus into -2, it becomes the 4. This is your addition. In the same pattern, here is the subtraction. After that, you have the scalar multiplication. Scalar multiplication means that you have the matrix A, like you are multiplying this matrix A with any number, like 2A, you are finding the 3A, you are finding the -3A, you are finding the -A, you are finding the 1 over 2A. You are multiplying the matrix with just a single number. Just look here, you have this matrix A, and you are multiplying it with -2. You are finding the -2A, which means that you are multiplying this matrix with 2. So -2 means that this -2 multiplied with every element of the matrix. This -2 multiplied with the 2, it will give you -4. This -2 multiplied with -3, it will give you 6. Minus minus plus 6, and this -2 multiplied with 1, it gives you -2, and this -2 multiplied with 4, it will give you -8. So this is the matrix scalar multiplication. Now I will teach you the matrix multiplication of two matrices. So if you have this matrix A and this matrix B, then how can you find the multiplication? I am taking the two matrices of same order, like this is the 1 2 3 4, and the other matrix is 5 6 2 1. So their multiplication is that. For multiplication, you have to remember one thing, which is the number of element, the number of rows, the number of columns in first matrix must be equal to the, this is the condition. If number of columns of matrix A, if number of columns in first matrix, which means that number of columns in first matrix must be equal to the number of rows of second matrix. Just look here, it has two columns, this one, and if the second matrix has two rows, then the multiplication is possible. But if you have like the matrix of this form, like you have the uh, this one, this thing like 1 2. So in this case you have two columns but you have one row. So you have two columns and you have one row. So here the multiplication is not possible. For multiplication, your first matrix have the column which is equal to the rows of second matrix. So this is the condition. So for this one, for this case, as I write here, for this case, this one you can multiply these two matrices. So how can you multiply? You just multiply this row with this column. Look here, you multiply this one with 5, it's give you 5, and then you put the plus sign. You multiply always when you multiply 1 with 5, then you put plus sign and you multiply this element with this 2, multiply 2 give you 4. And in the same pattern you multiply the this first row with second column. You multiply 1 with 6, it gives you 6, and you multiply 2 with 1, it will give you 2, with 1 it will give you 2. Now you multiply first row with first column and second column. Now you multiply this second row with first column and second column. You multiply 3 with 5, it will give you 15. You multiplied 4 with 2, it will give you 4 with 2, 8. And in the same way, you multiply 3 with 6, it will give you 18. And you multiplied the 4 with 1, it will give you 1. So your final results is 5 plus 4, 9, 6 plus 2, 8, and 15 plus 8, it gives you 23, and it's 19. So this is your multiplication. Now I am going move further. So here is some property. In matrix, you can, if you add a plus b and on the other side you add b plus a, the result is same. The next property is that this is called the commutative property. This is called the associative property. You can take three matrices a plus b plus c. You add first a plus b, then add in c, and on the other side you add a into b plus c. You add this one first. You perform this one and add it into a. We both have the same result in the similar matrix. This here O means that the zero matrix. Zero matrix means that it contains all the elements are zero. So if you add any a with zero, you get the same matrix A. So if you add a with minus a, you got the zero. So these are some properties. You don't have need to understand these properties. But here is the in matrix AB is not equal to BA. So in matrix you can say that the commutative property does not hold. But this is not as much important for you, and this is also not as much important for you. You have to understand just the operations on matrices, like how can you add, how can you subtract, how can you multiply with a matrix with a scalar number, how can you multiply two matrices. So until now you have understand some operation on matrices. Now I am teaching you the some more. These are the properties that I have discussed earlier, so you don't need to understand these properties. Now I am teaching you the transpose of a matrix. I am going towards the transpose of a matrix. Just wait a moment. So here, this is the topic on transpose of a matrix. So what is the transpose of a matrix? As I have discussed earlier, you have a matrix, this one. You change the rows into column. Like this is the row, you change into column, and this is the row, you change into column. It's just a simple thing. So these are some properties of a the transpose. If you take the double time transpose of a matrix, you get the same number. If you add a plus b, then you take transpose, and on the other side you take the a transpose and add it into b transpose, you get the same result. And remember this one, a b transpose is equal to b transpose a transpose. And he's saying that the determinant of this a transpose and the determinant of A transpose both are same. Determinant of A transpose and determinant of the matrix A is same. And the next one is symmetric property. If you take the A transpose, it gives you A. It's a symmetric matrix. If you take the A transpose, it gives you minus A. It's the secure symmetric matrix. So you can look here. This matrix A actually a symmetric matrix. One, you have this matrix A. Sorry, I have make a mistake. So this is the matrix A. He can say find its A transpose. So some here are the some properties of a transpose of a matrix. A transpose equal to A, we say that it's a symmetric. A transpose is equal to minus A, we can say that it's symmetric. You don't need to understand these concepts. So now I am moving toward the next topic, which is the inverse of a matrix, or grammar rule. Or determinant of a matrix. So in order to start the determinant of a matrix, so this is the determinant of a matrix of 3 by 3 as well as 2 by 2. So for 2 by 2 matrix, the method of determinant is very easy. Like you have this matrix 1, 2, 3, 4. You a this A determinant equal to this A, 1, 2, 3, 4. You put the straight line, then this A determinant means that you multiply this one with 4, it give you 4. You multiply this element with this, and in the same pattern, you multiply this element with this, minus, you put the minus sign, and then you multiply this element with this. 3 multiplied by 2 gives you 6. So 4 minus 6, it gives you minus 2. So this is the A determinant. It's very easy. You multiply these elements, then put the minus sign. You multiply these elements and do the calculations. It's a simple way. So it's very easy for 2 by 2. Now I am going to discuss the 3 by 3 matrix. In 3 by 3 matrix, I am showing you a case here. Like, look here, you have this matrix, this one, as you are looking on your screen. This matrix, like here, I am using some different. I think you should use pink color. 1, 2, 3, 0, -1, and here is 4, and it's 2, and it's 1, and it's 0. You finding it's transport. You finding it's you are finding its determinant. So its determinant is usually denoted by, you can say this is the matrix A. Its determinant is usually denoted by the straight line. So I am putting the straight line in order to save my time. This is the A determinant. This is the A determinant. So A determinant, while taking the A determinant, you put the A determinant here. You just write this number 1 here, put the two straight line, then put minus sign and write this number 2 here, and then put the two straight lines with space. After that, puts the plus sign 3, and then puts the two straight line here. Now, after doing these steps, just comes on this one. This one's just ignore the this row and this column. You got the this thing, put this thing into here, like it's give you -1, 4, 1, and 0. After doing this step, move to the next step, which is the this one. Now you are moving to the this number 2, this one number 2. For this number 2, you have to ignore this line and this line. You have to ignore the column and row in which the number 2 comes. The number 2 comes in second column and in first row. So you ignore second column, first row. You got these entries, which I am showing you by pink color, by black color. These entries and these entries. Now just write these black mention entries here: 0, 2, 4, and 0. After that, you have done this step also. Now after that, you are going to move the number. You are going to move on the number like I am using. Now this is the number 3. You ignore this see this line and this line, in which the 3 comes in third column and first row. You ignore the third column and first row. After that, you write this remaining thing, which I am showing here with some different color. Like I am going to use the green color. So this is the green one. This green portion comes here directly. It's 0, 2, -1, and 1. So now you takes A determinant equals to 1 into, you take its determinant, you multiply -1, 0, it gives you 0, then put the negative sign. Multiply 1 with 4, it gives you 4. Then you put this minus 2 same as it is, and you are going to write after that this one. You multiply 0 with 0, it gives you 0, and you multiply 2 with 4, it gives you 8, and then you put the plus sign 3. You multiply this 0 with 1, it gives you 0, and 2 with minus 1, it gives you, you put the minus sign and you multiply 2 with minus 1, so you got minus 2. So you got here 1 multiplied with minus 4, you got minus 2 multiplied with minus 8, you got plus 3 multiplied with 0. This minus minus becomes the plus 2. So here you got the minus 4, 2 multiplied by 8, it give you plus 16, and the 3 multiplied with 2, it give you 6. So 16 plus 6, it's 22, 22 minus 4, it will give you 18. So A determinant is 18. So it's very simple. I have teach you how can you find the A determinant. You have to write this number 1 and then put this one into here, and then we put minus 2 and ignore this one and this one and write 0 to 40, and then write the number 3 here and ignore the section that I have teach you earlier, and just write this portion. Just write this portion and taking the determinant of this one, and this one, and finally find the value of A determinant. So I hope that you understand the A determinant. So this is the technique of finding the A determinant. Always you find the determinant in this way. So if a matrix has A determinant 0, you can say that the matrix is singular. If any matrix A has determinant 0, we can say that's no inverse, which means that its inverse does not exist. And if A determinant is not equal to 0, we can say that its inverse exists. Its inverse exists, and okay, this is the two minor concept you have to understand and ignore these two steps also. Now I am going to teach you a trace of a matrix. What is the trace of a matrix? Now, the trace of a matrix, trace. What is the trace of a matrix? Just look here. You have the matrix A, which is the 1, 2, 0, 5. Trace of A equal to the sum of these entries, sum of diagonal entries, which is 1 plus 5, which is the 6. So trace of matrix A is 6. For 3 by 3 matrix, like you are looking on your screen, here, this one, in this one, you for trace, you can add these entries, which I am labeling with red color. So trace of A here is the 2 plus 2 plus into minus 2, it gives you 4 minus 2, which is the 2. So trace is 2. This is also a concept we use in our discussion. Okay, now I am going to towards the next topic, which is the A inverse, or you can say, okay, A inverse. So what is the A inverse and how can you find the A inverse? So here, okay, I will teach you A inverse when it is needed. So in this video, I have teach you what is a square matrix, a matrix in which number of rows and columns are equal, square matrix, rectangular matrix, and matrix in which the rows and columns are not equal. Then I have told you square matrix have some good properties, which means that we can find the inverse, determinant, characteristic polynomial, as well as eigenvalues, eigen vector for a square matrix. But there is a limitation for the rectangular matrix. We cannot find the inverse, determinant, or joint, characteristic polynomial, and the eigenvalue, and as well as the eigenvector. After that, I have teach you symmetric matrix. I says that if you take the A transpose, you get the matrix same A. We can say that A is symmetric. If I am taking the A transpose and we get the minus A, we will say that it's a symmetric matrix. And then uh, I have teach you the transpose of a matrix, symmetric and symmetric matrix, and then the determinant of 2 by 2 matrix, and after that I have teach you how can you find the determinant of 3 by 3 matrix. And the thing that I have not teach you until now, it's the adjoint of a matrix A and the inverse of a matrix A. So I will teach you adjoint and inverse when it's needed. Okay, so you have to understand this concept, and these concepts are useful for the discussion we have that we are going to discuss now. Now I am going to solve the problem like the eigenvalues, eigenvector that I have teaching you when in the previous class when my laptop battery ended. So here is the PDF form, the linear transformation. So here I have teach you until this one. So now it's easy for you to understand the things. So this is the matrix A. You have find its characteristic polynomial. You find A minus lambda I determinant. This is equal to P lambda of A, which is the characteristic polynomial. So you have this matrix and you put the lambda, and then this identity matrix of order 3, you put multiply lambda, lambda, lambda here. You might subtract this 3 minus lambda 0, 0, and 0 minus 0, 0, and 2 minus lambda, and this is 1 minus 0 gives you 0, 0 minus 0 gives you 0, 0 minus 0 gives you 0, and 2 minus lambda gives you 2 minus lambda. This one, after taking this one, you are going to find the A minus lambda I determinant. So you are finding this thing, which is the 3 minus lambda, and then 0, then 0, then 0, 2 minus lambda, then 1, and then 0, 0, 2 minus lambda. I have forgot this step. After this step, you just write this step. You puts the straight line here, straight line here, straight line here, straight line here, and you find the determinant, which is finding here by the method I have teach you. You take you write first you write this element 3 minus lambda, and you put the straight lines, and you ignore this one, and this one, this thing comes here, you shift this thing here. So 2 minus lambda 1 0, 2 minus lambda here, and after that you put the minus sign, and minus sign, and then this number 0, and you put the two straight line, and you ignore this and this, you got the 0, 0, and 1, and 2 minus lambda. So after that you put the plus sign, and this number, for this number you are ignoring the thus just this line and this line, you got 0, 2 minus lambda, and 0 and 0. So in this way you expand your matrix in this way. So actually this thing is 3 minus lambda, this 2 minus lambda, 2 minus lambda become 2 minus lambda multiplied with 2 minus lambda, and here 0 multiplied with 1, it's just give you 0, and this 0 makes the whole thing 0, and this 0 also makes the whole thing 0. So you have this one, you multiply all these terms, you got this polynomial. This is actually a characteristic polynomial. I am writing to save my time like CH polynomial, which is the characteristic polynomial. So after finding the characteristic polynomial, you have to put this characteristic polynomial equal to 0. You have to put p of lambda equal to 0. When you put this characteristic polynomial equal to 0, you got the eigenvalues. Like you get this polynomial or this one, you put it's equal to 0, then it's 3 minus lambda and 2 minus lambda, and 2 minus lambda, it's equal to 0. So 3 minus lambda equal to 0, you put 2 minus lambda equal to 0. So here lambda is equal to 3, and here lambda is equal to 2, and this when this is equal to 0, 2 minus lambda equal to 0, you get the lambda is equal to 2. So you got three lambdas, which is the lambda is equal to 2, lambda is equal to 2, and lambda 3. So these three are the eigenvalues. The values, lambda values are called the eigenvalues. And if you put these values into the set like 0, sorry, like 2, 2, and 3, then this is known as the spectrum of the transformation P. And this spectrum, if this spectrum contains the only real number means that it doesn't contain the I sign. Like this is the free of I. So this is the subset of real number. If it contains like 2 iota, then it's not a subset of real number. When our when our this spectrum, sigma t of C, is subset of real number, we can say that it's a diagonalizable. It's might be a diagonalizable. But if our this spectrum contains iota terms like which means that spectrum of TC is not a subset of a real number, uh, then we say that it's not diagonalizable. So matrix is diagonalizable if a spectrum is subset of real number. It doesn't contain the iota value. So this is the lambda, and we put this lambda into this one, and these are only the real numbers without iota. So spectrum is subset of real number. So now the algebraic multiplicity and geometric multiplicity. Algebraic multiplicity means that how many times a particular lambda value repeated. So you find these three eigenvalues, and this lambda is only one time. You got only three one time. Lambda is equal to 3, which means that algebraic multiplicity of this lambda, which is 3, is 1. And but the algebraic multiplicity of this number 2, or lambda equal to 2, is 2, because this eigenvalue lambda is equal to 2 comes 2 times. So its algebraic multiplicity is 2. In simple words, algebraic multiplicity means that how many times an eigenvalue repeated. If it's repeated for 3 times, we can say that the algebraic multiplicity is 3. So when you find the eigenvalues, our next target is to find the eigenvectors. How can we find the eigenvector? For eigenvector, we have to find this thing, a minus lambda I into v equal to 0. So we replace lambda values here. We find the 3. We put 3 here. Then we put 2 here. For this 3, we get the one eigenvector. For this lambda 2, we got two eigenvectors. So I am now moving further. So you find a minus lambda iv. So this is the a minus lambda iv. This is the minus lambda I, as you find earlier. U a minus lambda I into v equal to this one, equal to 0. You put this equal to 0. This is a minus lambda I. So you put a minus lambda I in place of this one. You put this matrix, which is this one, 3 minus lambda, which you have already find it. 0, 0, and this is the 0, 2 minus lambda, and this is the 1, and it's 0, and it's 2 minus lambda. And after that, you are going to multiply with the a, b, and c. And when you multiply it with a, b, and c, it's just a vector v. We suppose this vector v equal to a, b, c. It's up to you. You can take v equal to x, y, or z. So this is the v, which is the a, b, c, and it's just equal to this number. It's just equal to a 0 vector, which means that here we have this 0, this 0, 1, this 0, this 0. So this is the term is with a minus lambda I into v equal to 0. And this formula helps us to find the eigenvector. So now you have this general statement. In this general statement, you put lambda 3. It's up to you. You can put lambda 3 first or lambda 2 first. It's up to you. I am putting the lambda 3 in place of lambda. Here this 3 minus this lambda replaced with 3. It's 0. It's also 0. It's 0. It's 2 minus 3. It's 1. And it's 0. It's 0. It's 2 minus 3. It's here A, B, and C. And I am just give me a minute so that I will raise the screen. So here 0, 0, and 0. So now you got this thing 0, this 0, this 0, and this is the 0. This is the 2 minus 3, which is minus 1, and this is the 1, and this is the 0, 0, and here is minus 1, and then you have the A, B, and C, and after that you got here 0, 0, and also 0. Now you have got this system. After getting this system, you multiply this row with this row. So when you multiply 0 with A, you got 0. When you multiply 0 with B, you got 0. When you multiply this 0 with C, you got 0. So the first equation is means that 0 is equal to 0, which have no meaning. So ignore this one. So next one is that, okay, it's up to you. You are ignoring this one or just wasting your time for this step. But in the next case, you are multiplying this row with this column in the way that I am doing here. You are just multiplying 0 with A, it gives you 0. Then you are putting the plus sign. You are multiplying this minus 1. Now I am using the yellow color to show you this minus 1 with this number B. So it gives you minus B. And then you multiply this one with this C. You got the put the plus sign, and 1 multiplied with C, it gives you C, and it's equal to the 0. This first, when you multiply this with this, you got an equation. You put this equation equal to this number 0. And when you multiply this with this, you got the result, you put equal to this 0. And when you multiply this with this, you put it's equal to 0. So it's 0 multiplied with A, it's 0. 0 multiplied with B, it's also 0. And minus 1 multiplied with C, it's plus into minus C, it's equal to 0. From this one, C is equal to 0. So you have C 0. Now put this C equal to 0 in this equation. So when you put C 0 in this equation, you got the thing like I am showing in front of you, which is the nothing but the but here 0 plus into minus b, this minus b, and then plus c, this c is actually the 0. So it's 0 equal to 0. From this, b is equal to directly equal to 0. So you have b 0 and c 0. You got two values. So actually you have considered the v is equal to a, B, C, this one in the start. You have the A and B and C 0. So A is same as it is. You put B 0 and C 0. You have not find the value of A. If you are not have not find the value of A, then take A same as it is in B, and the value of B and C replace the value of B and C. So B is 0, C is 0. So here is A. Taking A common from this vector, you take V is equal to this A common. It becomes 1, 0, 0. So this is your eigenvector. We can say that it's V1. So for every eigenvalue, this eigenvector is for the lambda equal to 3. You find the eigenvector V1 for lambda is equal to 3. In the similar way, you are putting the 2 in this one. You are putting the 2 in this one. I am going to this show with yellow color. You are put 2 in this system. You got another two eigenvectors, and these two vectors are corresponding for the eigenvalues lambda is equal to 2. So I am going to find the eigenvector for lambda is equal to 2 now. So I am raising here the things. So just I am writing V1 here, V1 equal to 1, 0, 0. So after that, I am raising the other things that you looks on your screen. Just give me a minute. Okay, this one, this one, this one, this one, and this one, this one, this one. Okay, this one, and this one. Okay, so I have erased my screen now. So now for lambda is equal to 2, for 2 case, I am using the pink color here. You are putting the 2 here. It's 3 minus 2, it will give you 1. It's 0, same, it's 0, same. It's you are finding this thing a minus 2i. It's lambda replaced with 2, and it's v equal to 0, this thing. So it's 0, and it's 2 minus 2 0, it's 1, and then the same pattern it's 0, and it's also 0, it's 2 minus 2 0. So this ABC is same as it is here, or it's a 0 0 0. This case you are finding here. Again I am repeating, you have 3 minus 2, it's 1, and it's 2 minus 2, it's 0, it's 2 minus 2, it's 0. So clearly you got this system like here, this one. So dear, you have this, you multiply this with this, you got the a plus 0, a plus 0 plus 0 equal to 0. So this equation gives you a 0 from this one. And when you multiply this with first one, you got the c is equal to 0. So your a and c are 0. So you got the this vector b, this vector 0, v actually equals to a, b, and c, and you have find the a and c 0. So v is equal to 0, b, and 0. So you take b common, you got the 0, 1, 0. So this ab is here. So this is the v. So this is the vector v2. For lambda is equal to 2, you got only one eigenvector, which is the v2, which is this one. So the algebraic multiplicity. So this is the eigenvector for lambda is equal to 2. But listen here, if uh, if understand, now I am going to discuss the geometric multiplicity. What is the geometric multiplicity of number 3, this lambda 3? Geometric multiplicity equal means that how many linearly independent vector you have got for lambda. What does this thing mean? This thing means that when you are putting the lambda 3, you find eigenvector, which is this one, which is this one you have find this one. So you, for this only one eigenvalue lambda equal to 3, you have got only one eigenvector. So you can say that its geometric multiplicity of 3 is 1, means that for any particular eigenvalue, how many eigenvector you got. For this lambda equal to 3, you got only one eigenvector, which is 1, which is this one, v1. So its geometric multiplicity is 3. 2 which is 1. Sorry, it's 1. And in the same way, for this lambda equal to 2, you got the one eigenvector, which is v1, which means that for particular eigenvector lambda equal to 2, you got only one eigenvector, which is v2. So geometric multiplicity of 2 is 1. So geometric multiplicity of 2 is 1. Now, there is a very important concept. I am staying here 1 minute. I am writing a note here. Note, here is the note. If algebraic multiplicity of any particular lambda 1 equal to geometric multiplicity of this lambda 1 for all lambdas, which means that if algebraic multiplicity of a particular lambda equal to the geometric multiplicity of that same eigenvalue lambda, you can say that if this condition hold for every lambda, you can say that your matrix is diagonalizable. But if algebraic multiplicity is not equal to geometric multiplicity for even a single lambda, you can say that it's not a diagonalizable. In this case, in our this case, for this a, for this lambda is equal to 3, we have algebraic multiplicity of 3 equal to 1, because this lambda 3 becomes 1 time, and the geometric multiplicity of this 3 is also 1, which means that for lambda is equal to 3, you got only one eigenvector, which is the v1, this one. So algebraic multiplicity and geometric multiplicity of lambda equal to 3 is 1 and 1. So algebraic and geometric multiplicity is same for the eigenvalue lambda equal to 3. But there is a problem here. If I am discussing the for lambda is equal to algebraic multiplicity of 2, then it's 2. Why it's 2? Algebraic multiplicity means that how many times the eigenvalue lambda equal to 2 comes. It comes 2 times. So its algebraic multiplicity is simply 2. But the problem here is that its geometric multiplicity is 1. Why its geometric multiplicity is 1? Geometric multiplicity 1 means that for lambda is equal to 2, you just find one eigenvector, which is the v2. So geometric multiplicity of this 2 is 1. In this case, geometric multiplicity is 1, algebraic multiplicity of 2 is 2. So the algebraic and geometric multiplicity are not same, which implies that the matrix A is not diagonalizable. So you can write the statement the matrix A is not diagonalizable. So now I have a question from you. Think about this. What are the different scenarios that help us and that uh, gives us idea, that gives us trick, some methodology that are that that helps us to identify whether a matrix A is diagonalizable or not. The trick is very simple. If a matrix A is symmetric, then it must be a diagonalizable. This is the very basic. So first of all, you are checking your matrix. If matrix is symmetric, it's diagonalizable. The second thing is that if you are solving a matrix, you take a matrix, you find its characteristics, polynomial, you find its eigenvalues, you find three eigenvalues. Let's assume you find eigenvalue lambda 1, 2, lambda 2, 3, and lambda 3, 5. You take three eigenvalues, 2, 3, and 5. These eigenvalues are different, distinct. Distinct means that one is 2, second is 3, and the third one is 5. For every eigenvalue, you got one vector. Like if you have distinct eigenvalues, simple technique. If you have distinct eigenvalues, then your matrix A is diagonalizable. In this case, you have three distinct eigenvalues like 2, 3, and 5. For 2, you got one eigenvector V1. For 3, you got another eigenvector V2. For 5, you got only single vector V3. So for 2 V1, for 3 V2, for 5 you got the V3. So for three eigenvalues you got the three eigenvectors, which implies that your matrix A is diagonalizable. So I have teach you the three things. If algebraic multiplicity of a matrix equal to geometric multiplicity of a matrix, for every lambda, matrix is diagonalizable. If your matrix is symmetric, it's diagonalizable. If 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 you got the distinct eigenvalues, then your matrix is diagonalizable. If your if your eigenvalues are means real, which means that it doesn't contains the I term or iota, then your matrix might be diagonalizable. But when you are finding the characteristic polynomial, when you find the eigenvalue and you got any one of eigenvalue in the form of iota, you can simply say that it's not a diagonalizable. No need to move further. Okay, so this is the case for the diagonalizable matrix. So what is the diagonalizable matrix means, actually means? Diagonalizable matrix means that this is the process that gives us a diagonal matrix. Diagonal matrix, I am teaching you from the matrices portion. A diagonal matrix is a matrix in which all the elements are zero except the main diagonal, and at least one element of the main diagonal is not zero. So here, Uh, now I am going to discuss the question number 47, which is here the diagonalizable orthonormal basis. It's just the same like we have done the above question. So here, look here, just look here. This one, this one is your diagonalizable matrix. So I think so. I will teach you this diagonalizable basis tomorrow. So I am going to end the meeting now. Best wishes and watch this video for in order to make the basics on matrix and the diagonalizable matrix as well. And